In this video, we're going to discuss the dispersal of energy within a system, or the microstates of a system. This is about entropy and how we discuss the amount of entropy. How dispersed is the energy of a system? Let's imagine I have two particles. They're in a box and they're both moving at a starting speed. And it's the same speed. They're going to bounce around the container. They may eventually run into each other, though. When they do, depending on where they are, how close the container is, the angles, they may deflect and change the energies they each have. One might move faster, one might move slower. Let's think about that for a second. Let's imagine that I have these two particles, the green particle and the red particle. And they have an option. They could have no energy. They could have one amount of energy. They could have two amounts of energy. They could have three amounts of energy. Individual particles are quantum systems, so the amount of energy would be quantized. We're simplifying it here quite a bit. But let's say we have a system with two energy. Well, if they're both initially moving at the same speed, they would both have one of that energy. And so they'd both start with level 1. Upon impact, it's possible they bounce away at the same speed, but maybe one picks up the energy while the other loses it. You could capture one of them in a corner, and so just as it's bouncing, it hits the other one and just kind of gets stuck there as the other one gets launched away. Well, eventually the other one could come back, slam into the first one, and trade the energy back around. So you kind of have options here. Let's write it a little bit different. Here's particle, here's our purple particle, here's our green particle. And, well, I have two energy. So one of the options is they each have one. One of the options is 2 and 0, or 0 and 2. There's three ways we can spread that energy out. Now let's do this, but let's give it another energy. So we'll imagine the same system. Still got my two particles, one red, one green. This time I've got three energy. Well, I could have all three on one of them. So we'd have a purple up at 3. It could bounce into the green and lose a little bit and give the green 1. So I could have a 2 and a 1. I could bounce and make the green go a little faster and the red go a little slower. So it could be 1 and 2. And they could bounce and even launch the green a little faster as the red loses its last. And it could be 0 and 3. Having more energy gave me a greater variety of options for how to spread that energy out around my system. Let's go one more step. Let's put a third particle in. So let's imagine this, but I've got 3 particles. And we'll give them 3 energy. Well, they could, again, all be on one and none on the others. We could transfer one of it to green, or maybe we could have transferred one of it to blue, depending on if that red hit the green or the blue first. I could have spread it out evenly. I could have also started all the energy on the green. And that could have transferred, say, one of it up to the red, or it could have transferred one of it down to the blue. And we already did the one where they're all spread evenly. So we'll go next to what if it was all on blue to begin with. Blue could have transferred one of it to the green, or it could have transferred one of it to the red. And that's all of our options. That's all the possible ways that we could distribute 3 units of energy among 3 particles. Well, if we look for a minute, one of them having all and the others having nothing, that comes up 3 times. One of the particles having 0, one of them having 1, one of them having 2. Well, that comes up 1, 2, 3, 4, 5, 6. That comes up 6 times. And there's a single option where they're all evenly distributed. So of the possible combinations of spreading this energy out, the most favored is 2, 1, and 0. Reasonably often you could have all the energy on a single particle and the others not moving, and having them all have the same is really not likely. As they bounce around and transfer energy in between all these different combinations, well, the chance is that you're not going to end up with them all the same. You're going to have all the energy here. Green's going to bounce into, let's say, red, and it's going to either give one of its energy to red or it's going to give two of its energy to red. And so it's only going to show up in one of these states. Either of those states then could bounce into anything else and end up transferring in the energy to multiple of these other states. We can jump between them as they bounce into each other. So as the particles move around, they're constantly jumping between these. But a lot of them look fairly equivalent. As we said, a lot of these are just distributions of 0, 1, and 2. The idea of distributing the energy out over multiple possible combinations, how we can spread them out in all the different ways we can spread them out. These are microstates. There could be a lot more complexity that goes into microstates, position, velocities, things like that. But in a simplified view here, this is the idea. How did we distribute the available energy among the particles? Each of these is its own possible state. They are constantly changing back and forth. These are all the possible microstates. Well, when we think about larger systems, what we saw here is as we had more particles or more energy, we had more possible combinations. So by the time you're to a mole, the number of combinations is obscene. As a result, the number of distribution patterns that are likely all tend to be very similar. And so we see graphs like this that talk about the percentage of particles that have different amounts of energy. The reason these graphs work, why we don't have all our particles have just a single energy, or a few here, a few there, and a few there, is because of all the different possible combinations. When you have that many particles, they spread out statistically to be fairly average. And that is a key point of the entropy argument. It is a statistical argument. It says that the vast majority of the time it's going to be one of these equivalent states or one of the very close, nearly equivalent states. And by the time we're to this many particles with a whole bunch of energy, we pretty much always look the same. The chances of particles ever doing anything weird, like all having the exact same amount of energy, is basically non-existent. They're always going to be spread out in a fairly uniform fashion. Some will be a little faster, have a little higher energy. Some will be a little colder. The majority will be somewhere in the middle. So we've seen the idea of entropy hidden away inside graphs like this when we talked about things like reaction rates, where the energy of activation was out here and only some number of particles really had that. As all your particles bounce together, there's just a few that may have, say, enough energy to do some reaction. Most of the situations, none of them did. But occasionally a particle will have enough energy, and there's some percentage of them that will have that much. So we've seen this idea hidden away inside work before, but we're going to dive a little bit more into it. We want to quantify this. If you can have your energy distributed out among your particles, how distributed are they? How much energy are you distributing? How can that affect things? Entropy, given the S symbol, the amount of entropy is equal to the Boltzmann constant times the natural log of the microstates. So W here is the number of microstates. K is our Boltzmann constant. So you can calculate out the amount of entropy within a given system. But often we're not concerned with the actual entropy, we're concerned with the changes. As a reaction occurs, or as a chemical change occurs, such as a phase change, there's a change in the amount of entropy, a change in the distribution. So the delta S, that is equal to the S final minus the S initial. So think to salt dissolving in water. Your salt didn't have a lot of microstates to begin with in terms of positions within a container. If I got a large container with water and a block of sodium chloride down here, well, it did have vibrations and things. There was energy within the lattice of the solid sodium chloride, as the sodium chloride spread out, they just have a greater number of options. Their positions, their rotations, their trajectories, their speeds. There are more options as the sodium chloride dissolves. And as a result, it ends up with a greater entropy. It is more distributed throughout the system. This would have a higher final and a lower initial. And so we would find that it would have a positive delta S. When delta S is positive, we have more freedom of motion. When your delta S is negative, however, you have less freedom of motion. And while entropy in more complex systems can have many components, for a chemical system, we're generally thinking about the motional energy, the kinetic movements, rotations, vibrations. We'll dive more into that as we continue in these videos. This is when we talk about freedoms of motion here. That's about the molecules or the atoms or the ions able to move in more ways. They are more free than they were. They are more distributed among the possible combinations. Well, this is a factor in determining spontaneity. When you have a delta S, there are three types of delta S we have to consider. There's the delta S of the system, or often the reaction that we're watching. There's the delta S of the surroundings, and there's the delta S of the universe. Entropy must always increase, but that is only true for the universe. If a reaction or a process has happened, if a chemical change of any kind, a solution, a movement of gases into a new container, anything that happens that doesn't immediately just undo itself, there must be an increase in entropy for the universe. But the delta S of the universe is equal to the delta S of the system plus the delta S of the surrounding. It is possible to reduce entropy locally as long as we increase entropy somewhere else by a greater amount. So while we need entropy to always increase, it is not impossible to make entropy be less in a specific situation. We can think back for that to C6H12O6, our sugar. If we want to make sugar, if it's our product, along with 6 dioxygens, well, I've got to add 6 waters, I've got to add 6 CO2s, and I've got to add some light energy. Well, this was gas, this was liquid, this is a solid. So 6 gas and 6 gas. Gas molecules bounce around, they have lots of freedom. But as long as you have the same number of moles, it's not too different in terms of how much entropy they'd have. But I had a lot of water molecules that could move around, and I turn them into, in this process, I go down to a single molecule for that. There's a lot less freedom of motion in this. Forming sugar is going to be a negative delta S. This is disfavored for entropy. We are reducing the entropy of these molecules and atoms when we form sugar through photosynthesis. Why can we do it? Well, it's that light. Where did the light come from? It came from fusion. Fusion released enormous amounts of heat, which allowed lots of energy to permeate various molecules in the sun, causing them to get very excited and radiate that energy out and move and bounce. There was an enormous positive entropy increase from the sun. So to make that light, we had to have a huge positive delta S for the surroundings. So why is it that photosynthesis can occur, even though it's negative entropy to form sugar? Because the reality is that the entropy for the universe, the distribution of energy throughout all of everywhere, increased in the overall process. The sun created an enormous amount of energy as it fused hydrogens together, radiated that out in all directions. Some of that hit our planet and was able to be harnessed into a small local area, but only at the cost of a great deal of the fusion from the sun just going off in all random directions. And so the delta S of the universe was positive because the delta S of the surroundings, which was positive, was greater than the negative delta S of the system. So as long as the distribution of energy throughout the universe has increased to spread it farther, then we are able to perform reactions that locally caused it to be a little greater. Why does this happen if things are randomly distributing? Well, let's imagine really quickly, I've got a square, it has 100 pennies or energy units, whatever you want. And it's randomly going to spread out in a direction, left and right. What's going to happen is it's going to transfer half in both directions. So now I've got 50 and 50. Then I'm going to have these transfer up and down. So they're going to spread out. And this looks like the energy is spreading out. If you were to drop a drop of water, it spreads as it hits. If you take a rock and drop it and it falls, or you take a vase or something, drop it, it hits and the particles spread out. They bump into each other, but they tend to spread out from the center. However, as the next one spreads left and right, you can have some of the energy collide. So 12.5 is going to go this way, 12.5 comes in from that side, but this one is going to spread 12.5 over, and 12.5 in, they're going to combine to be 25. As the bottom does this as well, 12.5, 12.5, these are going to spread towards the center, and you're going to get 25 in the middle as the two come together. And now you'll have things go up and down. Well, as this one does this in the middle, I'm going to get 25 half, I'm going to get 25 in the middle, and 12.5 going down, 12.5 going up. If you ever see a drop of water in slow motion, and it presses down the center, and then the center kind of bounces back up, if you ever wonder why that is, as the energy distributes back and forth, well, this is a simplified view of it, inevitably it ends up bouncing off the things it's hitting and sending some of that energy back towards where it came from, which is what we just saw here. As these on the sides combine and spread their energy out in various directions, over time the energy will spread further and further out. But you can have local areas end up being significantly greater than all the other areas as things spread, just due to the random distributions as these are oscillating through and spreading out. The ability to locally have an increase is driven by pushing some of it much farther away. So the energy in this case distributes further throughout the universe in order to push some of that energy back into the center. This is a visual trick to kind of follow the idea of dispersing energy out in order to create a local higher source. Take this long enough though, the energy will spread out until everything effectively goes to zero. Entropy will maximize over time, and the final heat death of the universe will be when entropy is maximum, when it is as spread out as it can possibly be, with no more remaining concentrations. Luckily, we're looking at much smaller amounts of energy on a human time frame, and so we still have plenty of entropy from our sun and our planet to work with.